So let's look at an example. Up here, I've written out the brief equation that we would use to represent the divergence theorem. The fact that the surface integral along the boundary of the closed boundary that is a surface is equal to the triple integral over the volume where my function is the divergence of f. So in this example, we want to find the flux of the vector field, and this is my three-dimensional vector field given by zy x. And we want to find the flux over the unit sphere x squared plus y squared plus z squared equals 1. I wanted to recall, what does this vocabulary term flux mean? The flux is exactly this surface integral. The flux is the same thing as saying, I want to find the surface integral over some surface where in this case the surface is this closed unit sphere. So I'll say that this is the boundary dw of f dot ds. How would I compute this flux? How do I compute these surface integrals? Well, recall, and this is a formula that I think is an important formula to have memorized, or at least have instantly available to you. It's something that we've talked about a number of times, and it should be reviewed. The fact that this, first I'm going to have to parameterize this surface, so I need to come up with a parameterization of dw. So maybe I should write it out a little cleaner. dw needs to be parameterized. So I come up with some phi of uv. That's my parameterization. And then my formula here is going to be given by f of phi of uv dotted with, what do I dot my phi of uv with? I dot it with the normal vector. That's why it's important that we have an outward pointing normal vector, otherwise we would get a negative value. Dotted with the normal vector of my surface in terms of u's and v's, dv, du. And in this case, my integration would be the bounds of integration for my parameterization, where my v's could go from whatever value to whatever value, and my u's are going to go from whatever value to whatever constant value. I need constants on the outside. So this is my formula for computing the flux of a vector field, which is the same thing, the flux of the vector field over my boundary, which is the unit sphere. So if I wanted to compute this without using the divergence theorem, what would I have to do? First, I would have to parameterize my surface. I would have to come up with a parameterization of this unit sphere. I would plug it into my f function. I would also have to find the normal vector of the parameterization of my unit sphere, and then I could compute this double integral. So this is review material, and instead of doing that, one, I don't feel like coming up with a parameterization for a sphere. We've done it before, but it's really messy. It has lots of sines and cosines and cosines and sines, and then plugging that into here and taking a dot product, it's going to get really long. And the whole point of the divergence theorem is the fact that we don't actually have to go through all of this work. So instead of computing it this way, I'm going to compute it the second way. So the second way is to say, I'm going to compute the flux by using the divergence theorem. So first for the divergence theorem, what do I need to compute? I need to compute what is the divergence of f. And I made this example maybe overly simple to say, recall that the divergence of f is not a vector. Look, I almost wrote a vector symbol, not a vector. It's the partial derivative of the first component with respect to x, plus the partial derivative of the second component with respect to y, plus the partial derivative of the third component with respect to z. And let's look at what our f function is in this case. The first component is z, so the partial with respect to x is 0. The second component is y, so the partial with respect to y is 1. And the last component is x, so the partial derivative with respect to x is 0. Notice that you could get a function that's a function of x, y's, and z's. It might not be the constant 1. And that's okay, because we know how to integrate if we have x, y's, and z's. When we set this up as our triple integral, now we're taking the triple integral over w, which in this case is our sphere, of the divergence of f, which in this case is really easy. It's just 1. So what do I need to do now? I'm taking a triple integral over this sphere. What's the easiest way to integrate over a sphere? I could set it up in x, y, and z coordinates, but those are going to be really messy. That we have trouble looking at spheres in terms of those coordinates. So let's go ahead and use spherical coordinates. When I use spherical coordinates, well, I know that my theta in this case is going to go from 0 to 2 pi. My sphere goes in a full circle in the xy plane. My phi coordinates are going to go from 0 to pi. I want to trace out a full half circle in phi coordinates as I go in a full circle. And then my rho is going to go from 0 to 1 because my outer radius is a radius of 1 and I'm filling up the whole volume. That's why I want rho to take on all of those different values in between. Of 1 times, let's not forget our red, rho squared sine of phi, d rho, d phi, d theta. And now it's just integration. So when I integrate this with respect to rho, I'm going to end up with, keeping these as place markers, my outer two integrals, I'm only evaluating the innermost integral to start, and I get 1/3 rho cubed sine of phi, evaluated as rho goes from 0 to 1, which is just going to be 1/3. I still have my outer things, d phi, d theta. So notice that my sine of phi is going to stay, and my rho turns into a 1/3. So now I'm integrating the double integral of 1/3 sine of phi as d phi, d theta. So I just simplified that a little bit. Let's move over here and keep going. When I integrate sine of phi, that becomes negative cosine, so I get negative 1/3 cosine of phi. Evaluated as phi goes from 0 to pi. Recall that, with our outermost integral still in place, recall that the cosine of pi is equal to negative 1, and the cosine of 0 is equal to 1. So I end up with 1/3 negative 1 minus 1. Yeah. I think I messed up somewhere. Did I miss a minus sign? Oh no, sorry. I'll undo that in the film. So this becomes negative 2 times 1/3, which ends up being 2/3. Again, I still have my outermost integral. So now I'm just integrating 2/3 d theta as theta goes from 0 to 2 pi. And this integral becomes 2/3 theta evaluated from theta equals 0 to 2 pi. Of course, when I plug in 0, I get 0, and so when I plug in 2 pi, I get 4 pi over 3. That's my final answer. Let's look back and see if this makes sense. In this case, it does make sense. Notice that we're taking the triple integral over a value of 1. This really is just computing the volume of the unit sphere, which, if we remember our middle school geometry, we may or may not remember our middle school geometry, the volume of the unit sphere is 4/3 pi r cubed. And our r in this case is 1, so r cubed is just 1. So this was an easy way to be able to compute the flux of this vector field because the divergence of f in this case was something that was really simple. It was a scalar. Even if it weren't a scalar, it would give us values that are relatively straightforward to compute. And that's all that I have. Thank you so much for watching.